We saw before that the derivative of the position function is velocity. So that follows that the definite integral of the velocity function would be the position function evaluated at the limits of integration and subtracted, like this. So that's going to give us the change in position from time 1 to time 2. And a change in position is called displacement. So taking the integral of the rate of change of s gives us the change in s between the time 1 and time 2, which were the limits of integration. So that's the first general example. The second common example is finding the total distance traveled. So if you have a velocity function and you want to find the total distance, and total distance is different than displacement. So with displacement, you're finding just the difference between the starting point and the ending point of a particle. But it could have bounced back and forth a bunch of times in between and actually traveled a lot faster, or excuse me, farther than those two endpoints. So when you look for distance, you're going to find the absolute value of the velocity function, because remember, when a particle's changing direction, its velocity changes sign. So if we take the velocity's absolute value, we're taking the total distance it travels, and we're not considering that it turned around. So for this example, we're told that oil leaks from a tank at a rate of R of t gallons per minute at time t. What does this definite integral represent? Since R of t is a rate, when we take the integral of a rate, we're getting just the amount of oil in the tank. So therefore, the definite integral from 0 to 120 of R of t is going to tell us the amount of oil that has leaked out of the tank over an initial 2-hour period. That's how it's changed in those first 120 minutes. In the next example, we're going to look at combining the indefinite integral and the net change theorem. So we're given this acceleration function with an initial velocity between t equals 0 and t equals 3 seconds. So the first thing we're going to do is find the velocity at time t. So recall that the acceleration is the rate of change of the velocity. So we're going to take the indefinite integral of the acceleration function to find the velocity. So I take the antiderivative and I add the general constant c, and that's just my new velocity function. But I can use this initial value to determine what the real value of c is for this particular scenario. Using v of 0 equals -4, I see that c equals -4. So this is my velocity function. So now the next part of this example is to find the distance traveled during the given time interval. So this is where we use the absolute value of the velocity. To take the integral of an absolute value, we're going to split it up depending on where the function is above the x-axis and where the function is below the x-axis. So if you look at our function, our velocity function t squared plus 3t minus 4 on the interval 0 to 3, you see that part of it is below the x-axis and part of it is above the x-axis on that interval 0 to 3. So what we need to do is to account for the distance traveled between 0 and 1 second, we're going to find the integral of the negative of this part, and then add that to the definite integral of the area under this part between 1 and 3. So to do that, we're going to figure out what the zeros of our function v of t are, because that's where it's going to change sign. And my zeros are t equals 1 and t equals minus 4. So that's how I know to break up my intervals from 0 to 1 and 1 to 3. So I'm to find the absolute value of the velocity function. That's going to equal the definite integral from 0 to 1 of the negative of this part of the function. So this is going to give me positive values of the velocity, plus the definite integral from 1 to 3 of just the function, and that is just simply this part. So finding the antiderivative of each of those, I'm just using the power rule and I'm not going to talk through each one. This gives me 89 over 6 meters. And you can see that the negative area, which we made positive when we took the absolute value, is 2.16 repeating. The positive area is 12.66 repeating. And so notice that the when t is 3, the value of this antiderivative is 10.5. So that is the difference between the area below the curve, below the x-axis and above the x-axis. So in summary, there really wasn't a lot of new material in this except for interpreting the fundamental theorem of calculus a little bit differently when we're looking at the integrand of the function as the rate of change of the resulting function in our definite integral.